Welcome to Limiting Reagents and Percent Yield. Today we're going to be dealing with these two topics, but to deal with those two topics I want you to pay attention to a couple of the vocabulary terms that we're going to be listening to today. We're going to be paying attention to limiting reagent, theoretical yield, actual yield, and percent yield. In order to do this particular lesson, you are going to need some prior knowledge, mole to gram and gram to mole conversions, mass to mass conversions. These are both part of the stoichiometry, and balancing equations. So let's start with a really simple example. We're going to talk about calculating some cake. Cake basic recipes are flour, butter, eggs, sugar, milk, and baking soda. So let's look at our particular recipe. Our particular recipe is here: 2 cups flour, 1 stick butter, 4 eggs, 2 cups of sugar, 1 cup milk, and 2 tablespoons of baking powder. We can actually reduce this and put it into an equation, and for the time being I'm going to ignore all the cups, sticks, and tablespoons and just call them units. So 2 units of flour, 1 unit of butter, 4 units of eggs, 2 units of sugar, 1 unit of milk, 2 units of baking powder. All of this equals 1 cake. So how does that relate to what we're doing? Well, we need to calculate how many cakes we can make on this cake challenge. If you notice that I've put our equation up here, and down here is the amount of each ingredient that we have available. 50 flours, 10 units of sugar, 4 units of butter, 4 units of milk, 50 units of milk, 48 units of eggs, and 50 units of baking powder. To find out how much each unit will make, we simply take the number of units we have divided by the number of units required to make a single cake. So then what we do, if we divide these two, say 50 divided by 2, we know that we can make 25 cakes. If we do this for each ingredient, we find out the smallest number of cakes that we can make. So 10 sugars divided by 2 sugars, which is required in our equation, we end up with 5 cakes. Butter, we only need 1 unit of. We have 4 units. We can make 4 cakes. Milk, we only need 1 unit of, but we actually have 50, so we can make 50 cakes. Eggs, we have 48 of them. We need 4 per cake, so we can make 12 cakes. Baking powder, we need 2 units per cake. We have 50 units, so therefore we can make 25 cakes. When we compare all of these actual cake whole numbers, we know that the smallest amount, or the least amount of cakes that we can make is 4. So we can actually make 4 cakes. So which ingredient determines how many cakes we can make? The butter determines how many cakes we can make, simply because it has the least amount. So let's say we actually needed, let's say we needed 12 eggs per unit of cake. If we had 48, we would take the 48 divided by 12, and we would end up with 4. So eggs could also be could also be the agent that determines how many cakes we can make. But which ingredients are left over? So the ingredients left over in this particular scenario are flour, eggs, sugar, milk, and baking soda. The butter is considered to be the limiting reagent because that determines how many cakes we could make. And all the ingredients that are left over are in excess. We have more than what we need of those. So let's take a moment and write some notes down. A baker's recipe is similar to a chemist's equation. Both tell us how much of the ingredients we need. We can't complete any problem without a balanced equation. So in our particular case earlier, we had the 2 flour, 1 butter, etc. We wrote these as units simply because all chemical equations are written as mole units. And so sometimes we actually have to do those extra conversions from grams to moles in order to be able to figure some stuff out. And we'll get to that here in a little bit. The ingredients that determines how many products can be produced is the limiting reagent. Please remember that this is not always the smallest number. We could have had 5 butters and been able to make 5 cakes. But we could have had to have 12 eggs per cake and only had 48 eggs. That would have been our limiting reagent. So ingredients that are left over are said to be in excess. Let's go look at some chemical examples. Our sample problem in this particular example is sodium chloride can be prepared by the reaction of sodium metal with chlorine gas. Suppose that 6.7 moles of sodium react with 3.2 moles of chloride. We need to do two things. We need to determine what the limiting reagent is and how many moles of sodium chloride are produced. They give us the unbalanced equation of sodium plus chlorine equals sodium chloride. So the first thing we have to do is balance the equation. This particular balanced equation is 2 sodium plus chloride yields 2 NaCl's. Now we can go on to our step 2, which is to analyze part A. This is a really important step, although it seems maybe superfluous or like you've already got it, but it's an important step. So when we analyze, we determine our knowns and our unknowns. What we know. We know the number of moles of Na, which is 6.70. We know the number of moles of chlorine, which is 3.2. We also know from our balanced equation the ratio of sodium to chlorine. What don't we know? The limiting reagent. So let's go calculate that for part A. Remember, this isn't the end of the problem, we're just calculating the first part. So let's start with what we know. Sodium's our first one in the equation, so we're going to start with that, 6.7 moles of sodium, multiplied by the ratio, because we need to get from sodium to chlorine. So multiplied by the ratio that we've already predetermined in the balanced equation. Now we get to cross out because we have moles of sodium here, we have moles of sodium here. So that ends up crossing out. So now we have a math problem of 6.7 moles chlorine over 2. This will give us 3.35 moles of chloride. So let's go see what we can do with this. This calculation indicates that we need 3.5 moles of chlorine to react with that whole amount of 6.70. But we don't have that much. So we only have 3.2. Because we only have 3.2 of chlorine, we know that chlorine becomes a limiting reagent. We have more sodium than what we need, so that becomes in excess. So let's move on to part B. How many moles of sodium chloride are produced? So we have our unbalanced equation, which we've already balanced. So now we can analyze this. So again, let's find our knowns and our unknowns. We know that the amount of the limiting reagent is 3.2 moles of chloride. We know that, according to our balanced equation, 1 mole of chloride will give us 2 moles of sodium chloride. What don't we know is the number of moles of sodium chloride produced out of 3.2 moles of chloride. So let's go calculate that. So 3.2 moles of chloride is where we start, because that's the starting number we have. We're going to multiply that by our ratio, which is 2 moles sodium chloride divided by the 1 mole of chloride. We're going to cross out the moles of chloride on each side, and we're going to end up with a simple equation of 3.2 times 2 moles of chlorine, sodium chloride, so we end up with 6.4 moles sodium chloride. Fantastic! We know how much we can get. Now let's see if this actually makes sense. Did we do all this right? Let's think through this logically. So because our ratio is 2 to 1 of chlorine to sodium chloride, sodium should be in excess, and chlorine should be the limiting reagent. So all of this does make sense. So now we've dealt with a problem in which we didn't have to convert moles to grams or grams to moles. So let's take a look at this. I always want you to remember that words are important. So you have to pay attention to what the question is asking. This particular question was all in moles, but now let's go look at one in which the question is in grams. So this particular problem, copper and sulfur react to make copper 1 sulfide. If 80 grams of copper react with 25 grams of sulfur, we need to know what the limiting reagent is and what the maximum number of grams of copper 1 sulfide that can be formed. Remember, we're in grams. Our unbalanced equation right here needs to be balanced in moles. So let's go and balance that equation, which happens to be 2 copper plus 1 sulfur equals copper 1 sulfide. So that part we now have to analyze. We have knowns. We know our mass of our copper is 80 grams. We know our mass of sulfur is 25 grams. We know that our ratio is 2 moles of copper to 1 moles of sulfur. What don't we know? We don't know the limiting reagent, and we don't know how many grams of copper equals moles of copper, and how many grams of or 25 grams of sulfur equals how many moles. Luckily, we do know how to find grams to moles, so let's go and figure that out. So again, here's our unknowns. Let's start with copper. We want to find out how many moles of copper 80 grams equals. So 80 grams of copper multiplied by the ratio that we find in the periodic table of the atomic mass of copper is 63.5 grams. We know that equals 1 mole because we all found it on the periodic table. So we're simply doing some easy math here. 80 grams of copper, we multiplied by 1 mole of copper over 63.5 grams. Fantastic things, we get to cross out those grams of copper because when we end up with moles. When we're done with that, we end up with 1.26 moles of copper. That 80 divided by 63.5. So fantastic, we now know our moles of copper. But now we got to go figure out our moles of sulfur. 25.0 grams of sulfur multiplied by what we found out on our periodic table is 1 mole of sulfur over 32.1 grams of sulfur. We're crossing out here, so grams of sulfur, grams of sulfur. It's going to end up with 0.779 moles of sulfur. Fantastic, now we have everything in moles, which is what our equation is in. That's fantastic. But now we need to find out our limiting reagent. So let's start out with 1.26 moles of copper and find out how many moles of sulfur we actually need. So if we have 1.2 grams of, or 1.2 moles of copper, we actually need to multiply that by our ratio that we found inside our equation. So we know that for every mole of sulfur, we have 2 moles of copper. Fantastic. So let's go and begin to cross out what we can. And we find out that there's 0.630 moles of sulfur that react with 1.26 moles of copper. So what does this mean? Well, we have 1.26 moles of copper. We don't have any more. And we only need 0.63 moles of sulfur. We have more than that. So therefore, copper is our limiting reagent, and sulfur is in excess. So we compare the amount that we needed, figured all that out. Fantastic. So let's go on to analyze part B. So in part B, let's look at our knowns and our unknowns. Our limiting reagent, we already know, is the 1.26 moles of copper. We know the ratio of moles of copper to moles of copper 1 sulfur is 2 to 1. We know that 1 mole of copper 1 sulfide equals 159.1 grams of copper 1 sulfide. This is the molar mass. If you're confused about how I got this number, you might want to go back and review molar mass lesson. Okay? Now I need to know this. I put this in my knowns because we're going from grams to moles, from moles to grams in that stoichiometry problem. What I don't know is the mass of copper 1 sulfide produced in grams. So let's go and do some calculations. This is the big whole equation, but I'm going to walk you through it. So we start out with what we have. We have the 1.26 moles of copper. We need to take it out of moles of copper and put it into moles of copper 1 sulfide. The reason we're doing this is because our end unit is copper 1 sulfide, and it happens to be in grams, but our equation relates it in moles. So we start out with this 1.26 moles of copper. We're going to multiply it by our ratio of 1 mole of copper to sulfide to 2 moles of copper. We know that the 2 moles of copper go on the bottom because we're trying to get rid of it. And it's on the top here, so it's going to be on the bottom here. Our next step, since we've gotten to moles of copper 1 sulfide, is to get it to grams of copper 1 sulfide. We already know how to do this, but we're making this a bigger part of the equation. So we're taking moles of copper 1 sulfide, and we're going to multiply it by the number of moles the number of grams in the molar mass of copper 1 sulfide. We know that it's 159.1. We're able to cross some units out, some identifying units, so that we know that we're only left with grams of copper 1 sulfide. Our total equation ends up being 1.26 times 159.1 grams copper 1 sulfide all over 2. When we do this math, we end up with 1.00 times 10 to the second power grams copper sulfide. By the way, that's just 100 grams of copper 1 sulfide. So let's go do some evaluations. Does this make sense? Well, copper is the limiting reagent. We already made sure that that made sense. And the maximum number of grams of copper 1 sulfide produced has to be more than the initial copper because we added copper to sulfur. However, the copper 1 sulfide has to be less than the total grams of copper and sulfur because we had too much sulfur. So we know that this number is going to lie somewhere between the 80 grams of copper that we started with and the 105 grams of the two elements added together. So 100 does lie between 80 and 105, so we're in pretty good shape. Fantastic. Really, this isn't as hard as you thought it was if we break it down step by step. Now you know how to calculate how much of something is produced based on the availability of reagents, but we need to be able to calculate our yield. Yield is how much is produced. So let's go take some vocabulary time. Theoretical yield is the maximum amount of product that can be formed with a given amount of reactants. So in terms of recipe, this is going to be what it says on the box or on the recipe that says how much you're going to end up with. The actual yield is the amount of product that is really formed at the end. So maybe it's more or less than what you were told it was going to be. Now we also need to know the formula of how to calculate this. So percent yield is the actual yield, what I really came up with, divided by what I should have had, and this number is multiplied by 100% to give it a percentage. So let's go take a look at an easy example. Again, let's stick with the food idea. So a certain cookie recipe says that I'm going to produce 2 dozen cookies. However, when I make the cookies, and this always happens to me, I only have 20 cookies. What's my percent yield? Well, the first thing we need to do is analyze. What do I know? I know that the actual amount of cookies I got was 20. I was supposed to get 2 dozen cookies, and I know that 2 dozen cookies equals 24 cookies. So what don't I know? The percent yield. So let's calculate. I have this beautiful, beautiful plug and play formula, so that's what we're going to do. We're going to plug and play. I know that my actual yield is 20, my theoretical yield is 24, and then I'm going to multiply that by 100%. 20 divided by 24 is simply 0.8333. Then I multiply that by 100. I'm ending up with 83%. And I know you're already confused. Why do I only write 83% instead of 83.33%? Well, that's easy. The answer is significant figures. I only have 2 significant digits in 20 cookies. I only have 2 significant digits in 24 cookies. And I have 3 significant digits in 100%. I can only use the least amount of significant figures, so my answer must be 83%. So now we've done a simple example. Let's go look at a chemical one. I have calcium carbonate. It's decomposed by heating as shown in the following equation. Calcium carbonate yields calcium oxide plus carbon dioxide. So what's my theoretical yield of calcium oxide? 24.8 grams of calcium carbonate is heated. And then I want to know what my percent yield is if I actually come up with 13.1 grams of calcium oxide. So what's the first thing we do? We analyze. So I know that the mass of calcium carbonate is 24.8 grams. I know that 1 mole of calcium carbonate is equal to 1 mole of calcium oxide. Remember, we started in grams, we relate in moles, but our answer should be in grams, so I need to have all this stuff in here. 1 mole of calcium carbonate is equal to 100.1 grams of calcium carbonate. Remember, if you don't know how to do this, go back and check on molar mass. 1 mole of calcium oxide equals 56.1 grams of calcium oxide. Unknowns. Theoretical yield of calcium oxide equals how many grams of calcium oxide? So, to make sure we have all of this equation set right, we need to make sure that we understand we're going from grams of calcium carbonate to moles of calcium carbonate, because that's how our equation relates it, to moles of calcium oxide, out to grams of calcium oxide. So let's go look at that big, huge equation, even with all the crossouts, because we need to calculate. So here we have our starting point. We have our 24.8 grams of calcium carbonate. We need to multiply it out into moles. So here we have our 1 mole of calcium carbonate equal over 100.1 grams of calcium carbonate. We get to cross out our grams of calcium carbonate. So now we have moles of calcium carbonate. We need to relate it to the calcium oxide, and this is a 1-to-1 ratio. So we get to cross out moles of calcium carbonate. So now we have moles of calcium oxide, which is fantastic. And now we're going to, because that's our ending point, but we got to get it in grams. So then we multiply that by our conversion factor of 56.1 grams of calcium oxide. All of this was part of our knowns and our analyzation. So our big equation ends up being 24.8 times 56.1 grams of calcium oxide all over 100.1. When we do this particular math, we end up with 13.9 grams of calcium oxide. This is our theoretical yield. This is what the box says we should have. So now, let's go analyze part B, because now we're talking about our theoretical yield and our percent yield. It says we actually have 13.1 that's produced. So, we know that we actually have 13.1 grams. Our theoretical says that we should have 13.9. We know our wonderful plug-and-play equation. We need to determine our percent yield. So, time for calculations. Here's the big deal. We have the 13.1 grams over the 13.9, so our actual over our theoretical, all multiplied by 100. 13.1 divided by 13.9 is 0.942 times 100. That ends us up with 94.2%. This time I've kept everything because, all the numbers, I've kept them because we have 3 significant digits in our actual yield, 3 significant digits in our theoretical yield. So 3 is our magic number here. So does this make sense? Well, it should make sense. Our actual yield is slightly less than our theoretical yield. Therefore, our percent should be slightly less than 100. 94.2% percent yield is fantastic. So we know our answer should have 3 significant digits. I think we're doing really great. So now I'm going to give you an opportunity. We've worked through very easy problems to harder problems. And now I want to give you a chance for some extra credit. I want you to turn in your notes that you've taken over the course of this video. And I want you to turn in your correct answer with work to the problems that I have listed below. Turn those in and I will give you some extra credit on the limiting reagents and the percent yield assignments listed in your Brain Honey. Thanks and have a great day.